All right, so we still have TA support. If you got any trouble understanding the lab, you can feel free to reach out to the TA. And then the exam, I will reach out to you guys. We still have, including today, we got 3 more classes. So today, I want to finish the last bit about the inheritance, which is going to put everything together and also talk about polymorphic collection. That's really the goal for using inheritance. But we really have to pave such foundation in all the earlier classes to really understand what we're going to talk about today. So you guys really deserve this insight today, but we'll talk about it. The exam is going to be on the 14th. So I will reach out to you guys. Maybe I'll confirm maybe some details next Tuesday when we actually, in the last class. And then I can give you guys maybe some ideas about how you can really prepare for the exam. It's going to be cumulative, so you definitely should really study everything about the course. I'll speak more about it. And your written test number 2, it's basically graded. I'll release the result very soon, either later today or tomorrow early. You definitely will get the marks. And then if you got any concern about the grading, please don't email me. Just come to my office hour, and then we can talk about it. And during your exam period, I'll also try to host some office hour as well, so you guys can still talk to me. That's not an issue. Okay. I'll try to make myself maybe more available over Zoom if you really don't want to commute. That's understandable. Anyway, I'll reach out to you with details. And your last test for this course will be programming test number 3 that's going to happen this Friday. So today is Tuesday, and in about 3 days. So the guide has been released. Basically, the same kind of requirements. You're not supposed to use any programming library. And then it's about inheritance, so the coverage just about lab number 4. But it's also valuable if you can also redo practice test 2 as well. You might find some relevance as well. Okay, that's my tip to you. So you want to redo lab number 4. You want to redo practice number 2 if possible. And of course, the practice number 3 that I just released yesterday to you. You can take a look as well. So guys, as for the review session, it's still a little bit uncertain. I'm still communicating with the TA. I will put tentative just for now. Most likely it's going to happen for the review session. Most likely in person, you guys come to the classroom, and then the TA, most likely Micklin, she's going to go over the solution with you. But there could be some issues from our end, in which case we may not be able to hold it, but not very likely. But I'll confirm with you very soon. But for now, you can assume there will be a review session. And your lab number 5 is released. I kind of pushed the deadline to very late on the same week as the exam. It's not going to be covered in any of the assessment except for the exam. Especially for your lab number 5, as you will go through the instructions, there's some background study section about abstract classes and interfaces. So these 2 are the topics which we didn't get the time to really cover in our inheritance lecture. However, what you have learned so far will allow you to understand about these 2 concepts without any problem. I'll rather you guys actually graduate from this course with those 2 concepts understood as well. They are very natural extension or like a special cases about the inheritance that we speak about. But please go over the materials. I got slides there. I got also lecture recording, very good quality. You can go over them. They will be covered in the exam. All right, so that's also I said in the announcement as well. So abstract classes and interfaces. At the same time, when you're doing lab number 5, you also try to apply them as well. Right, so these 2 concepts will also carry you a long way beyond this class as well. Maybe in 2101, when you learn about data structures, you may have to use abstract classes and interfaces to implement your creations. All right, and for lab number 4, try to redo it. I think it's going to be definitely going to be helpful for your Friday's test. All right, guys, any questions? All right, good. Let's do some recap, and then we'll move on to the last bit about the inheritance. Last bit, which consists of multiple parts. That's the way to put it. It's not just a single topic, but hopefully within 40 or 50 minutes, we can finish that. We'll see. All right, so last time, we basically introduced this instance of operator. You can think about as far as this course is concerned, the reason we're using instance of is really for you to do safe typecast. Whenever you want to do a typecast like this, you are given some reference variable, x, and you're trying to cast x into type y. What that does is it's trying to, at the runtime, it's going to create an alias to the same objects as X dynamic type. However, the static type for that alias is going to be Y. All right, so that's something we spoke about. Compilation-wise, as long as this is either a upward cast or downward cast, it will compile. If it compiles, we can talk about runtime. In which case, we might run into class cast exception, right? That's really the condition you want to somehow understand intuitively rather than memorizing it. Because if memorize, somehow recall the wrong way during the exam, it's not very pleasant. Right, so the idea would be the dynamic type for X that's being cast must be able to fulfill the expectation on the static type of this cast type, basically, right? If it can fulfill, meaning that if the dynamic type is a descendant of Y that's being cast into, in that case, you will not run into any class cast exception. So we don't really have the written test anymore, but definitely the biggest one is coming for the exam. So you can definitely expect the exam will be quite inheritance heavy, right? So you really want to go through, you want to start going through everything that we spoke about the exam, starting from the different design alternative, the design principles, and also how you can use a super keyword, extends keyword, and also how we can understand about, expectations, static type, dynamic type, all sorts of things, right? These are all nice stuff that you want to really make sure you understand before writing the exam. Right, the instance of. And the instance of operator is not going to give you any like a pass or fail, it's just going to return true or false. If the expression here tells you true, that means it would be safe to cast X into Y, right? You can safely do that, all right? And we also try to visualize exactly, this kind of expectation from the instance of. You may also want to take a look at these three lines, even though they're a little bit symbolic, but they also summarize what you're supposed to know. Let's talk about very quickly. Inheritance, the fundamental stuff we talk about is about variable assignments or substitution. So whenever you got some substitution here, you want to make sure the right-hand side, its static type, is able to fulfill the expectation on the left-hand side, right? We talk about expectation. And also, we want to do some typecasting, and to really make sure the typecasting is actually safe, in the sense that you will not run into any class cast exception. You will have to check the instance of, right? That's also something we said. And you can really go over these three lines and can read through the description there. I think it really also summarizes what you're supposed to know intuitively. And this kind of an inheritance hierarchy, we didn't really go into how a tree itself is defined. It's really the topic they're going to learn substantially in 2101, the follow-up course. So now, just kind of get an idea that whenever you have some inheritance hierarchy, given certain class, you got the ancestor path, and also you got a bunch of descendants. You also got other classes which are neither ancestor nor descendants, right? So that's all you got to know. There might be some other terminology that's more advanced for trees that you don't have to worry about for this course, right? Just what we cover in the class. That should be sufficient. All right, and then we did a various example about instance of, right? You guys can just go over, and there's some exercise for you. You can also do them. The answer, you can find it also on the slides, right? Like if you got any trouble, you can let me know. Okay, all good. All right. And then I think these examples are just talking about when you declare the variable here with different static type. By declaring the static type quite higher up in the hierarchy, you kind of just having the minimum range of expectation, because the higher you are in the hierarchy, the less expectation you have for that particular type, right? And then here we try to declare the static type rather than smartphone. We try to lower that down into iOS. In that case, you got more methods to be called, because you're trying to do you're trying to go lower in the hierarchy. The lower you are in the hierarchy, the more methods you will get accumulated, and also new method you can add to the subclasses, right? It's all connected. All right, and then we also talk about this kind of expression here, right? You can see we are trying to do, okay, I'll make it bigger. So we are trying to cast SP into this particular type. It's a typecast expression. And then we try to surround that, wrap it within the parentheses and try to make a method call, right? That's also the anonymous cast that we spoke about earlier, just some more applications. Okay. All right. All right, call by value, right? So basically that's really the most important thing we spoke about last time. We try to recall what call by value really is. So you got the caller, you got the callee. When you are trying to call a method, you're basically passing some arguments. And this method here has its official declaration or API, the header of the method. That one there has certain type of the parameter. So here you got call by value means there's some implicit assignment that should be done as a first line. You don't really do that first line. Java runtime does it for you. But you want to know exactly what that line looks like. It's going to be the parameter is assigned to argument. As soon as you see variable assignment, you know that if there is some inheritance hierarchy in the context, you got to be watch out about the substitution, right? So this would mean the static type for arguments should fulfill the expectation of the static type for parameter, meaning that the static type for arguments should be a descendant of the static type for parameter. All right? So you can see this argument here. So in some way, we are not really teaching, we didn't really teach you anything new here. We're just trying to bring two things together. And this will be the kind of stuff you can expect on the exam. There might be certain topics we kind of learn in isolation in different weeks, but somehow they can work together, right? You might see them in the exam, right? So your safest bet is to really go over all the basic stuff in the iPad notes, in the slides, and then think through the issues, and then just deal with the problems, right, in the exam, right? Okay, call by value, and then we spoke about, let's say, student management system. We'll dive even deeper into the student management system. So last time we just tried to show to you about analyzing like a method call, right? I'll recap very quickly, and then we got to do more examples about this class over here. And then I'm going to draw some connection to the earlier non-inheritance design that we said is bad. And now that we have inheritance, we can see that having this kind of an array, you can see the array element type statically is the students. And students is at the top of the inheritance hierarchy. And because of polymorphism at the runtime, as we'll see, dynamically, each element can either be resident students or non-resident students, the descendant classes. That's exactly what polymorphism is about. Okay? So let's say here we got each element in the array will be of type students statically. And then we have different add method, add, and add. So one version will be taking resident students, another version taking non-resident students, another one taking students, right? So it turns out this one here is the most accommodating method, because in order to call this method here, you're going to call that, let's say, add. I'll draw it here. I'll just sketch a bit. Okay? You can look at the recording from last time for detailed discussion, but I'll sketch very quickly. If I want to call this method here, let's say, the way I'm going to call that would be, I'm going to say add students. And then I'm going to put some objects over here, right? In order for this method call to really compile, you have to recall the details about call by value. Because we know that this is the callee parameter, this is the caller arguments. The implicit assignment should be S is assigned to OBJ. So we should know that given that this is students statically, which is over here. And what can be OBJ static type? Any type that can fulfill the expectation for students, meaning that any descendant class of students should be okay. It can be students, it can be resident students, or it can be non-resident students, right? So that's kind of the logical reasoning you want to keep having in your mind, all right? And that's something we definitely spoke about last time, right? All right, so that's basically what I just summarized. You can also look at the detailed description from last time. And then that's the last exercise we did last Thursday, right? So it turns out, add students over here, where the parameter type is students. This is the most accommodating, because right now you can see given S1, S2, S3, RS, and RS, you can see they're all having different static type, but they're all descendant classes of the student parameter type. So that's why they will all compile. On the other hand, if you try to call add RS, that one there has static type for the parameter resident students. So only descendant class of resident student can be accepted, meaning that student cannot be accepted because it's ancestor, and also non-resident student class cannot be accepted because it's neither ancestor nor descendants, right? So these are the details you really want to recall. Right, a little bit long recap, but I just want to make sure you're on the same page. So when we continue with this discussion here about student management system today, hopefully that'll be better for you. All right, any questions? Yes.
My question is on static variables.
Static variable.
They are declared on the parent class. Are they inherited by the subclass?
The static variable, strictly speaking, does not belong to any, it's a good question here. The question is, will static variable be inherited to the subclass?
Yes.
I don't have a definite answer for now. I can look into it. Okay. Mm-hmm.
I was reading and I saw that there's certain, if you search online, they say that it's like they describe a parent class and a superclass as two separate things. What's the difference between a superclass and a parent?
Superclass and parent class are really the same. Really. It simply means if you say class A extends class B. In here, we say that B is A's parent class or B is A's superclass. So they are used interchangeably. However, you cannot say parent class is equivalent to ancestor classes. Ancestor classes are way broader. Ancestor will be your parents, your indirect parents all the way up, right? But parents will be the immediately above you, right? So parent class and superclass are really the same. So whenever you use a super keyword in a subclass, you're really referring to the method up just one level up. You cannot say super.super. You cannot do that. You can only refer to one level up. Mm-hmm. Okay. Yeah, it's a good question here. Let me look into it. Maybe I'll get back to you a little bit later. Also, the whole class. Okay. Okay. All right, if no further question, let's now move on to the stuff for today. Okay. Let's first of all, let's take a look at this example here. So let me just let you know which slides I'm talking about. I'm trying to talk about 4 slides at one go because they are somehow related, but somehow on a slide is more like a written form, so I couldn't really put it into a single slide. But on the iPad, I can do that. I should tell you exactly what to notice. But you should definitely study the slides as well. So it's going to be slide number 79 all the way to 82. Right, so you can definitely take a look at the details over here, but I'm going to talk about it as well. Right, so 79 to 82 is something I'm going to talk about right now. I'm going to talk about in a single page. All right. Okay, so again, so let's see what's the context over here. So we have our student management system. We got student, resident student, non-resident student. Right, that one we know pretty well. And let's consider this particular method in the student management system at RS, at resident students. So the static type for the parameter, which we call RS, right, is a variable that's at the method level. And the static type for that is resident students. All right? So now let's start with the following. First of all, if I try, let's say I created some SMS, student management system. That line compiles, no problem. Just want to create a student management system objects. And the first line I want you to take a look at is this. This one here. This one here. This one here. This one here. Think about these 4 code fragments, 1, 2, 3, 4, are somehow going to be compiled or executed separately. But when we discuss them, we just try to put them side by side so we can see the comparison. Okay? So you can see here, for example, if I have this SMS, I call this method here, where the parameter is resident students. And I'm passing different arguments. I just pass student S, student S, student S, NRS. Right? Got different possibility here. So now the question is it going to compile? Right? Okay, let's take a look at the first one, right? The first one here, I say add RS and then I pass S. Is it going to compile? Compilation. Actually, there's a cross here. That means answer is no, but I want an explanation for you. Can anybody explain why it will not compile? That could be I would consider the easy kind of question on the exam. Yes. Yes, definitely on the right track, yes. But I would suggest the way to put it is like this. I'm going to say that verbally. So here, argument S is of type students, right here, statically. And the corresponding parameter, let me say it again. The argument S over here, statically, students. And the parameter RS is resident students. And implicit assignment we are doing, because of call by values, RS is assigned to S. So this one here, static type, students. And this one here, static type, resident students. Is student a descending class of resident students? No. That's why it doesn't compile. That will be kind of the detailed explanation I would expect. So you definitely should mention about a call by value. You should definitely mention about the right-hand side is supposed to fulfill the expectation on the left-hand side. And then, accordingly, the right-hand side should be a descending class of left-hand side. If it is not, it doesn't compile. Okay? And similarly, you can look at other parts because static type 4 is simply the same, right? Students, students, students. So these other two lines will not compile for the same reason. And this one here, how about this one here? Is it going to compile? Also not, because the static type, this one I'll answer for you, right? Now, not wasting your time. So this one here, non-resident students, right? Can non-resident students, which is the static type of the arguments, fulfill the expectation of resident students, parameter type? No, it cannot. Because non-resident student is not even a descending class of that. They are sibling, neither ancestor nor descendants, right? They have no, in some way, no meaningful relationship for our concern, all right? So all these 4 lines, you can see they all don't compile. And you got to make sure you understand why they wouldn't compile. It's a very simple application of what we learned from last time, all right? Any question for the setup over here? Yes?
You mentioned you are supposed to mention 3 things when you're answering this type of question. You're supposed to mention the sentence or
maybe check the recording later. Okay, please.
Because
and then,
how would you want call by value? Because if you just say that, based on call by value, is that just you just get among?
you of course you got to mention call by value, but once you mention the call by value, you got to show that accordingly what would be the variable assignment that's implicit, right? And then based on that variable assignments, you want to see whether the right-hand side static type can fulfill the expectation of the left-hand side static type, right? And then you're going to answer accordingly whether in this particular case is it the case, right? Yeah. Okay. All right, so we know that all these 4 lines don't compile. So what we want to do is, can we at least trick the compiler to make them compile first? Yes, we can. We can do typecasting. What we learned from last Thursday, well, actually even last Tuesday, when we did that little exercise over there, we can basically cast one class to another arbitrary class that doesn't seem to have any relationship with it, right? Upcast all the way to the top, and downcast to that particular class, right? That's kind of the exercise we did. So getting compiler to really not complain about what you're writing is not an issue. So that's only the first step. Let's just try to make the compiler happy first, so at least we can get a chance to execute at the runtime. And then we'll talk about what's going to happen at the runtime. Okay. So what I would do is, so in these 3 here, because I know that the static type for the argument is simply just students. I know that simply passing S is not going to compile. Can I cast S to resident students? Can I do that? If you say I can do that, that's a compilation, right? Why can I do that? That's exactly right. So because resident student here, the cast type is a descendant class of the static type of S, which is student, we're doing downward casting. That's exactly right. Okay, very good. Okay, so let's make a note here. So this guy here is a downward cast. First of all, 2 things you should really know. Number 1, we're deciding whether you should compile or not. So number 1, it's a downward cast, right? Downward cast. Number 2, of course, it will compile. Okay. Oh, sorry. I really meant to write compiles. So it will compile. All right. So we do the same. We just basically replace this line here, replace this line here, and replace this line here, all by this line. So it's going to make the compiler happy. simply because the argument here all have the static type students. So we can all downcast to resident students. And another thing you should also know, if the typecast compiles, what will be the static type for that typecast expression? It will correspond to the cast type, basically, right? So number 3, which is even more important, because once you get number 3 there, you can further decide certain things. But anyway, so I'll put here. So number 3, the static type of the typecast expression is actually resident students. All right? Given that it is resident students, now let's check to see whether this method call should compile. Right? So this typecast expression here itself compiles. It has the static type RS. So now let's revisit call by value again. So we are basically doing this RS, which is parameter. So call by value is going to do, okay, I'll put it down here. So this one over here, okay, I'll put a star. So if you think about call by value, what we have is the parameter RS is assigned the typecast expression, which will be the R resident students and S. And we already figure out this typecast will compile, and that one there has the static type resident students. And for RS, that one there also was declared to be resident students. And this one here, static type, is also resident student, right? So resident student is a descending class of itself, so that compiles. By adding that typecast to the argument itself, it makes the method call compile. Okay? On the other hand, in this case, NRS didn't compile. What if we try NRS and cast that to resident student with the intention that the cast, if compiles, if, notice that I said if it compiles, the resident students will be the static type for the expression. That one there can match the resident student here. Will this work? Anyone? How come? Okay, very good. All right. So this one here basically is this. This NRS has the static type non-resident students. And you're trying to cast that into resident students. So to go from here to here, you're basically saying, I want to go from NRS to its sibling, neither upward nor downwards. So the cast itself is not going to compile. So it's not going to compile. Okay? Neither upward nor downward. Okay, so compilation is going to fail. Okay. Very good. All right, so this one here, basically the story is done. All right, done in the sense that if you pass NRS over here, it's not going to compile. Even if you try to do typecast, it's also not going to compile. But you should really know why. And let's revisit these 3 cases. If you only put S over here, that didn't compile. But now once we do the typecast, as we explained, it compiled. So now we have a chance to talk about runtime. What's going to happen at the runtime? Since we talk about typecast, right? So got to think about whether or not typecast expression is going to occur. Any idea? Let's say, for example, right? Let's say for this case over here, all right? If I replace this line here by this line over here, it compiles. Am I going to run into class cast exception? I saw somebody say no. I also saw somebody say yes. So cannot be controversial, right? Got to be one answer. Go ahead.
I think yes, because the dynamic type of S is student, and so the new, like the CAS type, resident student can't fulfill, the dynamic type student can't fulfill the CAS type resident student. So I wouldn't have an exception.
Okay, very good. Yeah, spot on. Okay, let me just repeat what your fellow student just said, so it's including the recording. Okay, so in order to decide, again, it's more like a review, right? In order to decide whether or not you got a class CAS exception, you got to see if the dynamic type of S, which is for student in this case, can it fulfill the expectation for resident student? You will only be able to fulfill if students is a descending class of resident student. Of course not. It cannot fulfill, right? So this will have class CAS exception. Yes, because dynamic type students cannot fulfill the CAS type, I'll say CT for CAS type, which is resident students. Because student is not a descending class of resident students. What about this one here? If I replace this line here by this line, it compiles. Am I going to have class CAS exception? All right, this one, okay, let's see. Dynamic type is right here, non-resident students. Can non-resident student fulfill the expectation of resident students? No, it's not a descendants. All right, I'll leave the, oh, I'm so sorry. I'll leave the justification to you. Sorry about that. Oh, wrong course. Okay. All right. So this one here, we are also going to have, yes, we're going to get class CAS exception. Because the dynamic type, which is non-resident students, cannot fulfill the CAS type resident students. All right. The final one. This one here, I'm pretty sure you can answer, right? Are we going to get class CAS exception here? No, because dynamic type, resident student over here, can it fulfill resident student? Of course, a class is always descendant of itself. Okay. So this one, do we have class CAS exception? No. Okay, and the reason I just explained. You can also write it down. All right, I think this example here is really nice because it really put many things together. You kind of put the method call, also you try to typecast the arguments, and also we kind of review about how you can decide about two different stages for typecast. Compilation, up or downward, and also runtime. You're gonna get a class CAS exception, right? Many things together, right? But you can also look at the slides. I think that will also give you a little bit more like a written form. All right, any question about this? Very good. All right, let's now move on. All right, so let's now talk about some stuff here. I think we'll go for maybe about 10 minutes or so, and then we should take a short break. This one is going to take a little bit longer, but let's take advantage of 10 minutes, and we'll take a short break. Okay, we should be okay. So the slides I'm going to talk about now will be slide 83. Okay, let me go a little bit of slideshow because there's a very important link. I really want you guys to really try and also compare and contrast when you go home today, when you do the study. I'll suggest you take a look at this contrast as soon as possible. Okay, let's take a look at the slide first and then I'll move on to iPad. We're going to do some tracing. Okay. So how do we define the student management system? Now we want to basically solve the problem there. The student management system should really collect both the resident students and non-resident students. If you recall about 6 or 7 lectures earlier, when we present that problem there, right, that's a problem we're trying to solve, right? We are solving it. And student management system here, right, the class, and notice that this is the solution with inheritance. There is only a single array, students. Students happen to be at the top of the hierarchy, right? Underneath it, we got resident student and non-resident student. If you like, you can also try to create another variant yourself. How about smartphone, right? For example, you can create a class called smartphone retail store, for example. And then over there, you can say you have an array of smartphone or an array of iOS, depending on what exactly you want to represent. But if you say you want to have a collection of all the phones together, you can say all the phones will be an array of smartphones, which is at the top of the smartphone hierarchy, right? Now we'll focus on something simpler just for the class. And then we got as student here, and one thing I noticed right away is this parameter type here really allows all the descendant classes of students, resident student and non-resident student. Whenever you call this method here with some arguments, the argument static type, because taught by value, can be a descendant of that, right? That's exactly what we just talked about so far, right? Before this slide. And then we got one method here called register all. That's something I'll also walk you through, right? We are going to just go over each element in the array, which contains either resident student or non-resident student, and we're just going to call the register method. Okay, something like that. And we can also calculate tuition as well. That's something I'll show to you. All right, that's the class, pretty simple, okay? So now the link I want you to really try is over here. You can see here at the bottom here, a collection of students without inheritance, right? If you click on that, this will bring us back to no inheritance solution. In which case, the resident students and the non-resident students, they have nothing to do with each other. They don't have a common superclass. In that way, what we have to do is we have to declare these two arrays separately. We have no choice. All right? Accordingly, we need to have two separate counters, and also we need to have like a two separate add method, and also we need to have like a two separate for loops, right? Etc. So depending on how many kinds of students you have, you will just need to repeat this kind of pattern over and over because you don't have inheritance. So this very severely violates the single choice principle that we spoke about, right? You're gonna make sure you review these two design principles. And that's really the version without inheritance, but if you click on that, a polymorphic collection of students, that's the one we're gonna talk about today to finish off the topic for inheritance, right? Because now we do have all the nice all the nice discussion about polymorphism, variable substitution, or sometimes even typecasting, things like that. So now we are properly equipped to actually do things that's more advanced. Okay. All right. Any questions so far? All right. Good. Okay. So I think what we should do now is let's now try to do some code tracing and then try to see what's going on here. All right. Okay. Let's now trace the code line by line. Let's do this maybe for about 5 minutes or so. I think that should be enough, and then we'll take a short break. Okay, let's do that. So let's start with this line first. Line number 1, 2, 3, 4, 5, right here. Okay, these 5 lines. Let's see what they're doing. We're basically creating two objects, RS and RS. RS and RS. Dynamic type, resident students, resident students. Non-resident students, non-resident students. And for the resident student RS, it has the premium rates, and we set it to be 1.5 premium rates. And for the non-resident students, it has the discount rate right here, and we set it to be 0.5. Okay, 1, 3, 5. We already visualize it, right? Just save some time. Two objects here. If you only look at these two objects in isolation, it's nothing challenging. But now, because of inheritance, thanks to inheritance, we will be able to store this and this together in the same array. Because the way we define or declare the, it's not, oh yeah, it's still here. The way we declare the array is right here, right? So this is very important, okay? Because here you can see the students array is students. So this is the static type of the students, I'll say SS, of index 0, index 1, etc. Right? So that's something you want to recall. And then we have this as students method, and the parameter is simply just students right here. Okay? So the fact that it is students, I'll remind you about here. Any arguments of the static type that's descendants of this can be used, right? Because it's call by value. Call by value, right? And this is where polymorphism really has a role, okay? Polymorphism. As we'll see. Okay, so with the single static type over here being students, but at the runtime it has different shapes, different dynamic type. That's possible in each element in the array. Okay, and then we have register all right here. Okay, so this particular example here, you can see the register method, right? If you think about the register method, let's recall very quickly. Okay, you can see that in the student class, we do have the register method, but somehow the register method was not overridden in resident student or non-resident students. So it's really a single version, not really multiple versions. So this method here is inherited verbatim to here. Also, it's inherited verbatim to over here. Right? Just notice that, right? Nothing wrong with that, just happened to be for this example. I think later on, maybe after the break, I got another example for you where depending on the dynamic type, we can try to call maybe get tuition. That one really can show that like a different version, right? I'm so sorry. I'm not sure what I pressed. There we go. Okay. Okay, there's polymorphism, and then you want to also highlight this part here about students at index I. As we'll see, this index I over here, statically, is students. However, dynamically, it can be descendants of students. And then, so now register is just going to call the version that's defined in the dynamic type. It can be calling the version from resident students. It can be calling from the version of non-resident students, even though it's got to be the same version. But conceptually, think about the class that's being called. I think it'll be better. Okay. And this is also the dynamic binding. We haven't traced the code just yet, but I'll do that in a moment. So you can think about a register that's being called really depends on the dynamic type of student I. Okay? Dynamic binding. Okay? All right, let's now keep going about tracing. Okay? So let's see this. So we have as students, and RS and RS, we are able to pass them and compile, right? Why they compile? We already explained. Okay? So what's going to happen here? So RS over here, right, you know pretty well from your previous lab. So let's say RS over here is going to call the, so that means S is now going to be replaced by RS, right? RS, something like that, right? So what you will do is, at the moment, the counter is actually 0. So that means we're going to store this particular object at index 0, right? In that way, we're just going to let it point to this particular object that's being pointed to by RS. Right? For the detailed tracing, you can definitely go over, but that's something we did earlier. Let me say one more time, okay, since it's been a while. When you execute this method here, RS is being passed right here. And the way to trace it is to think about every occurrence of S, the parameter is replaced by RS. In that way, we are assigning number of students at the moment should be 0, right? So that means index 0 for this array should be pointing to wherever RS, the argument, is pointing to. So that's why we have this pointer here. All right? So after this one over here, we are able to let the dynamic type for element 0 to be resident students. So this one tells you that dynamic type of the SS array at index 0 is resident students. Static type, still students. That one doesn't change. And we do something very similar. How about here, NRS? We're calling S students for the second time. So that means every occurrence of S is going to be replaced by NRS and also NRS. Right? Now the counter has been incremented by 1. So that means we're going to store at index 1 right here. And that one there is actually going to point to wherever NRS is pointing to. Right? NRS is the argument. Right? So now the dynamic type of SS at index 1 should now be NRS, which correspond to the dynamic type for the objects. So you can now see that for index 0 and index 1, their static type remain to be students, what's declared. However, the dynamic type is resident student versus non-resident students. But the bottom line, they are both descendant classes of the static type. All right? So these two lines are the most fundamental one. These two. All right? I would suggest we are basically almost done with this particular example. I just want to show to you how you can really run a loop to actually go over this array. So why don't we take a very short break and then we'll resume. Okay? All right, so let's continue with this example here very quickly. Not really, well, actually got to be, well, if you want me to slow down, I'll slow down, right? Because this is really important. So let's say we now have a course 2030. Oh, sorry. So the course 2030 over here, right? It's right here, right? 2030. Let's say the fee is just 500, right? Let's say. And then we have register all. All right. So this one here, basically you can, the tracing over here, you can actually definitely go through by yourself. But register all, if you actually go back to the slides, that one there is simply going to say, for every students in the array, we're simply going to call the register method on that. So if I call the register method on this student here, which is at index 0, it's just going to add this course into its array right here. Right? That one, if you do the tracing, it's going to happen like that. And also, if I go to the second, sorry, I just want to keep track of the time. If I go to the index 1, the second students over here, if I call the register method on that, it will happen the same way, right? Just add the course into their array right here, okay? So for register all, I will let you maybe try to trace by yourself. I will talk about the more confusing part, which is about calling the get tuition. Because the get tuition method, again, get tuition has been overridden either by premium rates in the resident students, or it may be overridden by discount rate in the non-resident students. Now we want to see that, given that our array over here, oh, that's something I also forgot to mention, okay, which is extremely important. So now, if you want to, let's take a look at element 0 and 1, right? I'll put a star. Okay, so this part here tells us that the static type of each element is students, corresponding to the declaration student right here. Meanwhile, that's point number 1. Point number 2, dynamic type of students 0 is resident students. Dynamic type of the index 1 at the same array is non-resident student. However, they are not really arbitrary classes. RS and also NRS, right? They are both descendants of the static type. That's really important to notice. So this one here and this one here, they are descendants of the static type students. And this is what we call a polymorphic collection. But in this case, the collection happened to be an array. This description here simply tells you that the students over here is a polymorphic Well, actually, see that term right here, right? It's a polymorphic array or collection. So one thing you want to know very clearly is, in order of, well, the greatest advantage about inheritance is you can have a single collection, which can be array, can be list, can be maybe a tree, can be a graph, you know, your later more advanced data structure courses. But having a polymorphic data structure simply means if you have inheritance properly set up, you can simply declare every element in the collection statically as the type that corresponds to the top of the hierarchy. Dynamically, at the runtime, it can be any of the descending classes. All right? So what's really so useful about this polymorphic collection? Basically, you have only one single collection declared. And then at the runtime, it's going to store the various different dynamic objects. But let's see how exactly that will work. So let's now go over this for loop altogether, right? At the moment, we have already 2 students, right? So at the moment, the number of students is simply just 2, right? You can see we got 1 student and 2 students, 2. So we know that it's going to run 2 iterations, where I is equal to 0, which will correspond to getting access to element 0. And the next iteration, index will be 1, so that means we're going to go over to this element here. Okay, let's talk about different iterations. So the I here, right here, is going to be either 0 or 1. 0 for the first iteration and 1 for the second iteration. And the get tuition over here, this is very important. Get tuition here, if you only look at this, you want to ask yourself, is it going to call the get tuition just about calculating the base amount? Or is it going to be this version here using the premium rates? Or is it going to be about this third version there using the discount rate? We don't know until the runtime. Okay, so let's take a look. So now for iteration number 1, okay, when I is equal to 0, okay, when I is equal to 0, so now we just talk about 0 here, right? I just also wrote down some expression you can think to your mind and also something you can also check as well. So this will be, okay, so here. So this will be the I value, so this will be iteration 1. So iteration number 1, you can see for the instance of, if you recall when I said the definition for instance of, the left-hand side can be any expression denoting some object, right? Not necessarily just a reference variable. So you can see we got some sms.ss, which is an array at index 0. So it's really referring to index 0, this object over here. And we're asking this object here, instance of all these 3 classes. Now it's a little quiz about what should be the value for each of these 3 instance of operations. True or false, basically, right? We even recap about what instance of really means, right? Today in the beginning. What should be the true and false value for all the 3 instance of evaluations? Give it a try. It's okay to be wrong. One hint to help you, in order to evaluate the instance of, should we worry more about dynamic type or static type? If you're not even sure about that, okay, watch out, right? Because instance of is only going to be evaluated at the runtime. So that means you have to worry about dynamic type. So what you should really look at is the dynamic type for the left-hand side. All right, let's now take a look. It's okay, you know, we can go slowly on this because that's really important. So if you look at this one here. So, okay, let's say this. If you look at just this part here, array at index 0 is pointing to this object, dynamically resident students. So we know that the dynamic type is resident students. So instance of is going to return true, it's going to evaluate to true if the resident students can fulfill the right-hand side. Can resident student fulfill non-resident students? No. Can it fulfill itself? Yes. Can it fulfill students? Yes. It's a descendants. All right? So that means we got false and we got true, and we got true. Question about this? It can. That's why it's true, right? You mean why it can? Because resident students can fulfill student because resident student is a descending class of student, right? Yeah. All right, that's the first iteration. And then for the second iteration, we are actually going to increment the value of I to 1. So now you can see we are looking at basically SS1 right here, right? So instance of is also going to be evaluated depending on what's the dynamic type at this point, right? So that one there is really the index 1 that we are talking about, right? Index 1. All right, guys, your turn. What should be the value for each instance of? Used to be false, true, true. What about now? Ah, good. Sounds good. Good. All right. So because dynamic type now is actually non-resident student, right? So dynamic type is non-resident students, right? Apparently, non-resident student can fulfill itself, but it cannot fulfill this, but it can also fulfill that, right? Very good. So it's going to be true, and then false, and then true. So you will see that you want to see that the instance of evaluations are different, right, between the iterations, simply because we're looking at expression over here of different dynamic types. I could be 0, I could be 1. When I is equal to 0, dynamic type is resident students, corresponding to this. When I is equal to 1, dynamic type is this, non-resident student. Okay, last thing to mention. So we understand pretty well about how the instance of checks can change its result dynamically between the iterations, where you are iterating through some polymorphic array, because every element there may have different descendant class of the static type. So now, let's consider this get tuition method, right? So now we can talk about which version is going to get called. When I is equal to 0, dynamic type is resident students. So when we call this method here, it's going to invoke the version that's at resident students using premium rate, right? When we move on to the second iteration, I is going to be incremented from 0 to 1 right here. And then we are now looking at the non-resident student dynamic type. So get tuition, invoke on the dynamic type because dynamic binding is going to use this discount rate. All right, so let me summarize it right here. So this one here, iteration number 1, it will be the resident students version, which uses this premium rate. And then we got iteration number 2, which will be the non-resident students version using the discount rate. Okay, of course, you're going to calculate differently. You know, for example, let's say this one here is going to use 1.5 times 500. Right? Second iteration is going to use 0.5 times 500. Right? All right, any question here? This page here is so important because it shows you how you can build a polymorphic array using a method where the parameter is basically at the top of the inheritance hierarchy when you build the polymorphic array or polymorphic collection. Once you have done that, the second concern will be about how the dynamic binding is actually going to work. So if we look at this method called over here, get tuition, is going to call different version depending on what the dynamic type is at the runtime. Okay. We're going? We're good? Good. All right, one more example, and then just a few more. Just a list of small things. At least we can finish about inheritance. 3 more things. Okay. So that's about polymorphic method parameter using call by value. Let's now talk about return type. Because you know that when for accessor, you will put the class name, some class name there to be the return type. What if that class name happened to be somewhere in some inheritance hierarchy? Right? That's something we're going to see. Okay, so we are done with this polymorphic array, student management system. That's okay. That's something we, oh, actually, this one here. Okay. So polymorphism, return type. Okay, let's talk about this one here. Okay, good. So let's now go over this quickly. Okay. So let's say we still have our student management system class and we still have our student array. Just remind yourself, we got student right here. Okay? And also we got as students. That's how we built a polymorphic array. That's something we just talked about, right, in the previous page. Let's now consider a new method. All right? Let's say we have some method called getStudents. And that one there is actually, that method there is actually going to take a integer. And I here may or may not be a valid index for the array. If it is not valid, well, let's say for example, let's say in this particular case, valid index will be 0 and 1. Anything larger, less than 0 or larger than 1 is going to consider as illegal arguments, in which case we'll throw some exception. All right? So that's why you will see something like here. So we say if it's not valid, we try to throw some exception accordingly. If it is valid, in that case, we simply say, so this is how we do it. Okay? So this is the return type. All right, so the student here is the return type. And then the S over here is some local variable. Just to make it a little bit easier for you to understand what's going on, I declare the type of this local variable just the same as the return type, students, just the same. Okay? And then we have this variable assignment here. What we do is SSI, the array at index I, what's the static type? Students, right? Right here. And we know that S over here also declared to be students. So we know that this variable substitution will compile. Student, of course, can fulfill itself. All right? Eventually, we simply return S. And now, let's recall what we learned from the previous page. SSI is a polymorphic array. A polymorphic array. For example, the example we did in the earlier page, at index 0, dynamic type is this. At index 1 is another dynamic type. Okay, I'll mention that detail here. Polymorphic array, for example, SS at index 0 and SS1 has the dynamic type resident students, and then versus non-resident students, right? They're different. So this means the S, which is going to be returned, is also itself polymorphic. What do I mean? Here, I declare the return type as students, statically. At the runtime, this return value here can be from some index in some polymorphic array, meaning that the dynamic type for the return value can either be resident students or non-resident students. This is what we can see just by seeing how the method is being declared. But we're going to see exactly how that's going to happen, right? But what you want to really note down for now is this variable assignment here tells you that the return value eventually is actually going to take some index from index elements from the array. But because the array is polymorphic, so the dynamic type for S is not fixed. It can be any of the descendant classes of students, basically. Okay? So now we're just trying to show to you polymorphism doesn't happen just at a method parameter. Also, it happens at the return value as well. Okay, let's take a look at this one here. Okay? So we have 2030, the course object here. we got RS, we got NRS, and we set up their premium rate and discount rate. Also, we register the 2 students, right? Exactly the same as before. Okay, actually what? I think this part here, we don't need to repeat. That's exactly what we spoke about earlier. So let me just see this one here, right here. You can think about this block of code right here builds the polymorphic array just right here, right? That's exactly the stuff we just spoke about in the previous page, okay? And let's now talk about specifically this method here, get students, all right? So we are comparing 2 lines. This will be line number 1. All right. And this will be line number 2. You can see the difference is in line number 1, we are passing argument 0. In line number 2, we are passing argument 1. Right? So now, let's think about just by considering this variable substitution. Is it going to compile? All right? We are assigning something on the right-hand side to the left-hand side. So what's the static type for SMS.getStudents? Students, right? How do we tell? Look at the declaration of getStudent, just student. Look at the declaration only, okay? So we know that this expression over here has a static type, students. Similarly, this one over here, even though we are trying a different index, but statically, it's also students as well. So you can see whether students can fulfill itself, whether students can fulfill itself. Of course it can. So variable assignment-wise, it's okay. How about at the runtime? At the runtime, if you try to step into this one here, right? So if I try to step into this method call, and then I will get into here. And then eventually it's going to use the value 0. So that means the I over here is going to be 0. What would that do? That one there is going to retrieve the objects from index 0 in the array, resident students, right? So that means dynamically, this one here is going to be resident students because it's going to retrieve the SS array at index 0, which we know is a resident student objects. Okay? Similarly, if you consider this line here, statically we know that this expression here is simply student. Dynamically, if you try to step into this method call, right? If you step into it, that one there means we're going to use the I here, index 1. Index 1 here is pointing to an object dynamically non-resident students, right? So that's going to be the dynamic type that's being returned. So this one here, dynamic type will be non-resident students. This is the most important part to really notice for this example, right? Let me recap, and then the rest will be very similar as what we said earlier. By declaring the return type of an accessor being a class somewhere in the hierarchy, polymorphism tells you that at the runtime, the dynamic type for the return value can be any of the descendant classes of the static return type. In this case, resident students or non-resident students. And the way to really trace this code is to look at which elements at which index is being returned from the polymorphic array. It could be from index 0, in which case you got this. It could be from index 1, in which case you got this, right? Depends. So that's why this block of code and this block of code will be executed differently. I'll just give you one example, okay? So if you look at just this line here. So look at this line here, s.getTuition, and also s.getTuition right here, right? I'll make it a little bit bigger. Okay, so s.getTuition here, which version is it going to call? Because the dynamic type of s is resident students. So call the version that's in resident students. So this will be the resident students version. On the other hand, how about here? S.get tuition. So in that way, we can see as the context objects is being reassigned to the return value of get students at index 1. That one that we know is going to return non-resident students. So we know that it's going to call the version that's in the non-resident students. Okay, so this one will be the non-resident students version. Okay, and you can also try to check the instance off as well. Okay, that's something I'll leave to you. Instance off, and then etc. Another line you also want to look at is here. This one here. Okay, the final line. We know that the static type for this get students is going to correspond to the declare type, which is right here, get student, right? That's a static type right there. So we know that the right-hand side is the students. Can student fulfill non-resident students? No, it cannot. So this line here is something that you should really judge right away. It does not even compile, right? Because students statically cannot fulfill its descendants. It cannot, all right? So this page over here and also this page over here contains so many details about polymorphism, dynamic binding, and also all sorts of basic detail tracing that we covered early in the course. You really want to take a look at these two pages carefully. Okay. Okay, let's now go a little bit more. Okay. Let me skip this for now. May not have time today, but let's now talk about the equals method very quickly, right? I may just do this one as part of the like a recap on Thursday, but we can definitely talk about recursion on Thursday. Okay, let me just do this one here. Okay, that's a final example about overriding, and then we're basically done with the inheritance. Okay, that's the polymorphic return type we just spoke about. Okay. All right, so this page here basically just talk about when should you consider static type, when should you consider dynamic type. That's something I kind of wrote down on the iPad notes earlier, but it's just another reminder. And as I promised, I'll talk about how you can read this table, maybe on Thursday when I do a recap. But let me spend about 3 minutes to do just one example. So let's talk about the equals method. We're just talking about if you got multiple versions of the equals method along the ancestor path, which version should you call? The best way to illustrate this would be, let's look at the example here, okay? So let's say we got 3 classes, okay? We got A, B, and C. So the B extends A, C extends B. So we got A, B, C, like that. Okay? And in this case, we do actually want to put object in the context because we want to talk about the equals method, for which every class inherits from the object class. So that's why we put it here. And if you recall, we got a default version, right? And in this scenario number 1, A, B, and C all choose not to override the equals method. They all want to use the default version. Okay? So what we have is we got C1 and C2. Okay? So C1 here, you can see it has its dynamic type C. Right here. And C2 has its dynamic type also C. And we try to say C1 that equals C2. Now, which version of the equals method should be called? This one should be straightforward because there's only one version, right? It's kind of easy for you. But you got to be careful when you do the reasoning because you should really look at the dynamic type for C1. First of all, dynamic type for C1 is C. That means we should really call the version that's defined over here. And this one here, it does not really, it does not explicitly override the equals method. So go up 1 level to B. B also does not override it, go up 1 level. A also does not define it, go up, that's already the top, right? So go to the object directly. So that's the version. Okay, that's the object version. We'll do a few more variants to just show to you. Okay. So the equals method that's going to be called will be the object version. Okay, right here. All right, let's see another variant here. Let's say we have class C overriding the equals. Other setup remain the same. So we still have C1, the dynamic type is simply just C. And the answer now should be also very straightforward. So now if I say C1 dot equals C2, which version should be called? C, right? Because C1 has dynamic type C, right? That one's also very easy. But let's see the last one, okay? Bear with me. So C1, yeah, give me 2 minutes. I can get it done, okay? So dynamic type over here is C. So the version that's going to be called will be C. That one also is very easy. Now this one here, all right? This one here basically saying that only B, somehow in the middle, overrides the equals method, okay? And then we still got C here. The search process will just be the same. So when we say C1 that equals C2, C1 does not explicitly override it, go up one level. And B has it, we found it, done. Don't do any further, all right? So this one here is basically just version B. Final one. Oh, no final one. Let me give you one. And that'll be it. Okay, let me give you another thing to think about. Okay, and let me call that number 4. So let's say I also got Boolean equals in A as well. So we now got 1, 2, 3 versions. Now, which version should be called? Still B. The principle is you basically choose to find the equals method that's overridden in the closest ancestor. And remember, ancestor including the class itself. If the method is already overridden in C, that's the closest one. Choose the one in C. If no, get to the next closest ancestor, which is B. If it has it, that's it. You don't go any further. Okay? So I'll write it down and then we're done. So the B will be the overridden version in the closest ancestor. All right. All right, so the only thing I haven't really covered is the table that's kind of symbolic. I'll do that as part of the recap on Thursday. All right, so we are basically done with the inheritance. I would suggest try to start reviewing all the stuff that we spoke about inheritance, and then starting from Thursday and next Tuesday, we'll talk about recursion.